I can say what you said.
No, a nosotros nos afecta. Nosotros no.
Y si hablo aquí ya se debería decir. Bueno, hablo aquí y ya está. Okay.
And we are already being transmitted. So, hello everybody, we are starting, and I will give the first space to local organizer and to the host. And yes.
Okay. Well, thank you everyone for being here in person and online. It has been a while. I remember being in Malta some time ago.
100 years ago.
Yeah, with the closing borders of government in Malta to Spain and a crazy week. So it's really a pleasure to be here in person. We plan to have this informal working group meeting. Welcome everyone in person and online. If there is any problem online, please let us know with the chat. I want to first of all thank Rosa Donat, Vice President of Innovation and Transfer. I don't know if I translate properly, Vicerrectora de Innovación y Transferencia, recently elected, and also Salva Moll, Dean of Faculty of Mathematics, for giving us this institutional welcoming. So I let you the word.
Good morning. I'm delighted to welcome you to the University of Valencia, in person or online, as participants in this meeting of the working group number 1 of the European Cross-Faction G2Net, a network of people with different but complementary expertise that had decided to join efforts in order to advance science in capital letters. As you all know, the research groups on computational astrophysics and cosmology and computer-aided modeling of astrophysical plasma, both working at the University of Valencia, form part of the team that announced the detection of gravitational waves in 2016, an unprecedented scientific achievement that was the result of the collaboration between many scientists in different countries. New achievements will surely come from being able to combine techniques that can handle the incredibly enormous amounts of information contained in the full electromagnetic spectrum with the expertise of people working on gravitational waves, which is precisely the expertise of the people that participate in this meeting. A meeting that the University of Valencia, a public university with more than 500 years of continuous support to the advancement of science, is very proud to host. I wish you all a pleasant and productive meeting. For those of you here, please enjoy the time with friends and colleagues after these troublesome pandemic times. And please do find the time to enjoy our beautiful city, Valencia. Welcome to Valencia. Welcome to the University of Valencia.
Rosa, it is my great pleasure to welcome you all on the Faculty of Mathematics of the University of Valencia in this opening session. I think that it is the first time I will hold an event of this type in terms of multidisciplinarity. It's true that 3 years ago, this university held the International Congress of Industrial and Applied Mathematics, ICAM, which was a great success and of which we are very proud. However, that meeting was only about mathematics and applications to real life of our discipline. This is not the case now. In the G2 networking group 1, one can find mainly experimental or theoretical physicists, astrophysicists, computer scientists, or electrical engineers. However, and this is the good news with the mathematical community, in your group there are also a few mathematicians. It may happen that in your countries, such a collaboration between so many disciplines and experts in many different things is not unusual. Here in Spain, it's not the case. At least in the last century, the majority of the mathematicians in Spain have worked among our own groups, far away both from the applications and, what is more shocking, far away from the rest of the science. Let's try. Okay. The hyper-specialization of the research leading us to work in only our small particular field without looking at science in a broad way. Let's try this now. But now, fortunately, things have changed, and we have realized that we cannot be working alone to do real progress in science. And you know this fact better than me. Among the keywords in your action, I can find some of the most relevant challenges in your fields: big data, machine learning, neural networks, neutron stars, natural language processing, or data mining, for instance. When creating this working group, you realize that you have to work together so as to profit from your cutting-edge research, because it might be more difficult or even impossible to progress if you try to do it alone. However, in your memorandum, I read as areas of expertise relevant for the action, physical sciences with gravitational astronomy, computer and informatics sciences with machine learning algorithms, and physics of Earth interior with seismology. After reading this, I miss mathematics. Mathematics is at the core of any of these areas of expertise, not only as the language of science, but as the key to understand or to interpret the results obtained. For instance, understanding the algorithms, finding when they will prove to be successful or when they will fail is among the tasks of a mathematician. And we can all benefit from this cooperation. Your research brings us new challenges in mathematics, especially in geometry, partial differential equations, and statistics. New problems that we have to understand and to try to build solutions, in 2 words, new mathematics. It is only working together that we could progress in understanding the universe that we live in. Thank you very much for having chosen our faculty for celebrating this meeting. We are very honored. Special thanks to Isabel Cordero for bringing all of you here. And please feel like at home and enjoy your stay here. Finally, let me conclude by wishing you great days of intensive and fruitful work.
Very much. I may add, mathematics is at the core. It's such a core of this thing that we even didn't think about mentioning because it's so obvious, right? I would say yes. And also that's why we are meeting here, because it's the place. We are all connected by mathematics. All right. Okay. So thank you very much for this invitation and welcome. And now we are moving into more pragmatic and let's say group-related tasks. So I will give a small summary and the presentation of the group and what we will be doing currently. Sometimes how to make it full screen. Can you make it full screen? Sure, you want to like Control L or R. It's not a color reader.
You have to open it with a Chrome, not with.
So maybe I'm a little bit OCD one. Yes.
Let's check the first one.
Okay, thank you. Okay, so this is just a small summary of what are the group goals and what are the plans for this meeting. So I'm speaking on behalf of the Annalisa too. She's connected. Annalisa, I hope you can hear us also. And if I'm saying something wrong, please interrupt. So
sorry, hello to everyone.
sorry.
Hello to everyone. I just wanted to greetings everyone.
Okay, so Annalisa is greeting you, but can you make it a little bit louder, perhaps? Or people from abroad, from remote, maybe if they want to comment, maybe we should somehow hear them. Okay, that doesn't matter. I will be repeating your questions if you have any. All right. So just a summary of the group, let's say, skills and also tasks. So we have this is the one of the three groups in this construction, the one that is probably the largest one. It's related to applications of machine learning in gravitational wave astronomy. And here, of course, this is not a simple kind of goal. We have several different approaches, and as you can see, we have many members. Currently here, I see like 20 people, but let's say like another 10 is connected. Taking part, yet another 20, I would say. So we have 50 people in the group that basically display all kinds of various skills, not only related to gravitational waves directly, not only related to data analysis directly, but also to computing in general, and all kinds of time series analysis, image analysis, this type of things. It can be applied in principle to gravitational wave astronomy. So at the beginning, we have defined this type of 4 tasks that are related to either accessing the data and exploring the optimal representation that can be used to data analysis, the detection, classification, parameter estimation of the gravitational wave data. Third task that was related to specific techniques, denoising, because you know that gravitational waves are immersed in noise mostly all the time. And the noise is not easy. It's not a wide Gaussian noise, but it's non-stationary, non-Gaussian, not wide, and transient phenomena happening all the time. And the parameter estimation I already mentioned. So, and I would say that we are doing well in this respect. Although maybe not, it's not maybe how to say related using related vocabulary from the machine learning experience. It's not a supervised thing. I see that the tasks are accomplished, but without a strict supervision, which is maybe even better because people are working in their domains. We are meeting from time to time and exchanging information. So this slide is just to show you that we are meeting every month. There are links to agendas and minutes. We have 2 other working groups in this constructions related to seismic activity, seismic noise, and also to control systems. So we have potential synergies there. We already started to also advertise our action in this kind of maybe not a very straightforward way, but actually I think it's quite successful in Kaggle. There was the first Kaggle competition for the compact binary coalescences signals. That was quite well received. There was another one prepared by the Hanover group. I think Andrzej will be talking about that at some point. There is another one that we're planning to prepare. Maybe we'll now deal with a different source of gravitational waves, not transient like this one, but a more continuous source. That are also that are not yet discovered, but very promising sources of gravitational waves that are long-lasting, persistent gravitational waves. And so, in summary, we have already produced, looking at the acknowledgements of papers that are available publicly, more than 60 papers in this action. So I think we should continue. This is working well. Okay, so this is a slide that maybe deals a little bit about the problems that we may have. Maybe there is not enough kind of communication between us. From my point of view, as a coordinator, maybe we should meet more often, maybe contact more, maybe have some more tools, other tools that we are using. And I hope that we will discuss this during this meeting, because it's there's always something that we can improve. But now I will slowly move to, or maybe not slowly, but faster, to what we will be having here. So we have 2.5 days of progress reports, plans, already finished things. This is the link that one can access the timetable. We'll have several discussion sessions, especially today. We will have one that is related to the paper that we would like to write, the kind of old G2net paper, but because of the fact that the WG1, our group, is the largest, we have to take some sort of a decisive role in this, I think. At least deciding about what we want to do as a group and what is our goal in this paper, and then of course discuss this in other working group leaders from other groups. So this is today in the evening, and then more kind of not directly related to work, but more pleasant stuff is the famous G2net movie that we will have the I would say kind of a premiere tomorrow, and there will be some sort of a round table and discussion related to this. And there will have also another kind of networking kind of get-together session on Wednesday. So that's that. Yes, and then so there is talked about that, the WG1 input into G2net paper. These are some things to be discussed and either kind of implement or invent something else. But this is what I and also Elena and others thought about what we should do in this work. I think we should kind of start really doing it, because to be more or less done with it at the end of holidays, summer holidays, which is then we have to somehow be more or less ready, more or less around the beginning of the holidays, only polish these things between September. So these are a few points that we will be discussing today, I hope. Just flashing this now so that everybody are aware of this. Okay, this is my last slide. So more or less this is the plan, and maybe I will give you some time to comment on this, or we can move directly to the talks. Does anybody has any comment at this level, at this point? And of course, I mean, I would like this meeting to be really informal, so don't worry. Interrupt me, interrupt everybody else, and so on. Okay. Any comments or questions from remote? No, I cannot hear anybody. Okay, so let's move to the first talk then, if there are no questions now. And one should not clap, I think. This is kind of so, all right. So we are using this. Yes. Maybe you can attach this somewhere.
Actually, the end of the bullets.
Or maybe on both.
Can you hear me? Yeah. I think I prefer to hold it.
Okay, so let's move the notice to
That's what I guess.
And this is also already visible on outside.
Hi. How are you? I'm a bit nervous because it's actually my first, well, I would say second in-person talk after a long time. But now there's more gravitational wave people here. So yeah. So my name is Melissa, and I'm here to present our work on simulating transient noise bursts in LIGO with generative adversarial networks. So first we wanted to talk a bit about what transient noise is in LIGO. So they are also called glitches. So they are caused by different things like instruments and the environment, and they are known or unknown, like their causes. They also come in a very broad forms, morphologies, frequencies, and everything that you can imagine. And they are pretty annoying, and I guess most people here know that, since they can diminish scientific data available and also hinder gravitational wave detection, mask or mimic gravitational waves. So here I have two examples. So this example here is of a flip glitch that's actually very similar to this high mass binary black hole. And here there's another glitch that it's completely covering or partially covering gw170 So of course we want to first understand more about them and also get rid of them. So the motivation of this work is to actually create an open source interface for producing time domain glitch waveforms, comma for that. So what we're going to do is to generate glitches in time domain with a method called generative adversarial networks to use in different applications of machine learning or other types of analysis. So we intend this to be open source completely. So for this talk, I will present the method. I will present some applications that we came up with, but we intend this to be very general, so many people can come up with other applications, of course. And finally, we are going to present our video packets that people can actually use for their applications. So let's start first with a data set. So for the data set, we focus on blip glitches from Livingston and Huffer, as well from LIGO data, because we're using O2. But I think the idea in the future is to move to O3, where we have more glitches. But we started with flips because they're simple and they're quite abundant. And also, as I said before, they're similar to other gravitational waves, as you have here the same example. So something important is that they are between 30 hertz and 250 in this band. So that's going to be relevant for later. So the problem that we have now is that the noise will hinder our machine learning algorithm, because this type of glitches, they are surrounded by non-structured noise. And well, if we have something that has no structure, our machine learning method can learn from it, right? So the question now is if we can actually separate glitches from noise. So the pre-processing that we do to have some type of smooth signal that the generative adversarial network can learn from is actually quite complex and a bit hard, in the sense that first we need to select the glitches with primitive SPI, which is a machine learning classifier, if you're not familiar with it. After that, we reconstruct with base wave, which is a wavelet reconstruction. So we obtain an input like this one here, like the blue one. But actually, all is the reconstruction. But you can see here in light blue that there is something that's very high, like very high frequency. So we don't want that, because in principle, blips are between 30 and 250 hertz. So this will be some artifact caused by the reconstruction itself. So we actually want to do some type of denoising and reduce the amount of noise here, because we want to minimize this contribution. So for that, we use RROF to try to minimize this. And once we have passed this base wave reconstruction, you can see here that it's a bit smaller, but the blip is more or less the same. So that's good, because we are only taking away high frequency contributions. For more details, you have here the ASD in the y-axis, and in the x-axis you have the frequency. So you can see the light blue, which is this part here, it's pretty high. But then if we pass it through ROF, then it's kind of minimal, which is the orange line there. But also the blip, the part that the blip is actually like a delta function, is more or less the same, except a high contribution, which is kind of minimized, which is exactly what we wanted. So this kind of helps, but of course it can happen that we denoise too much, so then the blip simply kind of disappears. So to test this, we actually re-evaluate the reconstructed denoised blips before inputting to the GAN, just to have some control of if the blip looks still as a blip according to gravity spike. So then we put that in the GAN and we train it. So what is a GAN? Well, GAN are used to learn the underlying distribution of the data. So it's a game between two networks. You have a generator and a discriminator. And the game is as follows. The generator generates from random noise some samples that are false. And the discriminator tries to tell them apart, if they are real or fake. So the idea is that at the end of the training, the discriminator actually has been completely full. Like it doesn't recognize anymore what's real or what's fake because the generator has learned the underlying distribution of the data. So this type of has been inspired by game theory, and it's a very unstable process because games in general are unstable. So here we use a particular type, which is Bassistin loss GAN. So we actually use Bassistin loss instead of mean-square error, for instance, which has a nice particularity, and is that allows us to train this discriminator till optimality, and that translates directly on very high quality of generated data. But again, this is a very unstable process, so we actually need to penalize the network to stabilize it a bit. And in our case, we actually pick CT-GAN that has some penalizations that I will talk about in a bit, and that's the paper if you're interested. So we implemented that in time series, because actually this one is for image generation. So CT-GAN has 3 penalizations: gradient penalty, consistency term, and dropout. And in the paper, you can go all about the mathematics behind. But here, I'm only going to give some intuition because of the experiments that we did. So here you have the loss of the discriminator and generator, and the consistency term and the gradient penalty. So they are learned by the machine learning algorithm. So you can see here that both of them go to 0, the discriminator and the generator, which is what we actually want. But there's some kind of instability here that we're trying to stabilize. And we compensate that with these 2 terms here. That's why the peaks look kind of similar to here, because we are penalizing when they are not stable. So the gradient penalty, it basically balances the loss between the discriminator and the generator. The consistency term regularizes the generator actually, and then we use dropout only the discriminator, and dropout only regularizes the discriminator. So the point is that if both terms, consistency term and gradient penalty, tend to 0, then we are pretty much stabilized. So once we have trained again, that of course takes a while, we can actually build a fake population of blips. And we can see here some examples. But because we are using a real data set, actually we have anomalies like this one here that doesn't look at all like a delta function or a blip. So the question now is if we can actually distinguish reliable blips, good generations, from fake and bad generations from like anomalous generations, right? So for that, we are going to use some metrics to avoid misgenerations. So the idea is that we define a metric, which is a distance measure that is going to represent the similarity between 2 signals, Bi and Bj, which in this case are 2 different blips. But we have a population of blips, actually real blips and fake blips that we will describe in a bit. So if we want to compare a population against a given blip, we are actually going to measure all of the population comparing to this blip that we want to see if it's good or not. So basically, we are going to take after that the mean and the standard error of the metric that we have. So what's M exactly? So here in this paper, we actually use 3 different metrics. They are basically all the same. They're just distance functions. So we use bus system distance, a match function that might be more normal for some people, and the normalized cross covariance. But in the end, they are all actually distance metrics. So after that, we actually want to know if our GAN, now that we have the metrics, we want to know if the GAN has learned the underlying distribution of the data. So the assumption is that the GAN actually has learned the underlying population of the data, except for certain anomalies, as we saw before. So the point is that if our blip that we generate is reliable, then it will represent both the real and fake populations, because the GAN can actually reproduce the real population. So their metrics will be more or less the same, and it will be more or less 1, which means that they are very similar. On the other case, if BJ, if it's an anomalous blip, it will not at all represent both real and fake populations. And the metrics will be around 0, meaning that they are completely different. So the hypothesis is that the similarity between a real population and a given blip and the fake population and a given blip are linearly correlated. So now we'll show some results that you have here. So in the x-axis, we have the comparison of the fake populations against itself. So comparing all the fake blips with all the fake blips. And in the y-axis, you have the comparison of the fake blips against the real ones to see if they are actually similar or not. So this is for basis time distance, match function, and normalized cross covariance. And why do we have 2 lines? Because actually we split the blips with a Livingston and Hanford. So this one should be Livingston and the other Hanford, and more or less they are the same. So what you can see here is that they are very linear. Actually, I can tell you that the Pearson coefficient for this is almost 1. So most of the blips are in this area. So for basis and distance, this means that they are very similar. This is completely the opposite. So the similar ones are here. But we can see some anomalies in the tails. So this is going to be relevant because in the end, you can just put a threshold and tell, well, I think these are anomalous, but the rest are reliable. And then it can actually be something that the user can change manually. So now that we are able to tell apart anomalous from non-anomalous, we are going to briefly describe some of the ideas that we have. So to use this type of work. So one of them is glitch population statistics. So here we simply took principal component analysis, 2 components, and put all the fake blips there. And also we cluster them. And you can see that we have 3 different clusters. That's because we chose it. That has some nice form. And also probably you cannot see it from there, but there's some stars that are here. Those are the ones that we label as anomalous because of the previous metric. So we can actually tell apart anomalies simply by looking at the slope, actually. Something else is to do a glitch template bank. And this was a small investigation of using a singular value decomposition, where in the x-axis here you have the error of the composition, like comparing the ground truth against the composition of SVD, and here are the probability densities. So you can see that if we pick 10 decompositions, more or less, we get back the actual blip. And this is actually used by test-lab, so we can implement something similar to what's happening with test-lab and do perhaps a glitch template back. Something more obvious are mock data challenges. We can generate glitches, like in this study here, and input them for our applications. And also something that to me are actually related is new glitch detection and improving glitch classification. So we can, because we are able to tell which blips are anomalous and which ones are not, we can always give feedback to the classifiers of glitches. And also that can improve the classification, or we can classify them better, like with new glitch detection, and we can maybe discover new glitches, which is always good to understand them a bit more. Oops. Oh, wrong button, sorry. So because at the very beginning I said that I wanted this to be flexible, you can color resample and rescale your glitch to your desires. So here the CTGAN is generating a whiting glitch, but you can color them with your favorite PSD. And actually here there's an example of a blip that it's actually this generation, but it has been colored with ET-PSD. You can, of course, resample your glitch. That's kind of trivial. And then you can adjust it to the SNR that you want. In this particular case, it's 10 SNR with the ET-PSD. And you can adjust this because of this alpha parameter, which is a scaling factor. So once you have the blip that you want, you can always insert it in colored noise, and then you can whiten it and use it for your application if that's what you want. So we said before that we are going to select the reliable generations. So here we have the metrics. A big change because now we're using 1 minus the match and 1 minus the cross variance, but they represent the same. So here will be something that's reliable, and here will be something that's anomalous. And you can create the percentile and say, well, I want everything between 0 and 1, or 0 and 0.9, and then you get your generation, and that can be tuned manually. So you can do this at home, and this is a practical example. You just go to this repo that soon it will be available for everyone, and you can get Gangly, which is a package that we are generating here. So you import it, and here you choose which population you want for Livingston, for instance, and then you get the whitening glitch, and then you can color it and put the SNR that you want according to your PSD. And this is a whiten example. And we also have some examples where you can run it and try it out if you want to. So this is the last slide, conclusions and future work. We have actually generated blip glitches as proof of concept, which is nice. We generated blips that represent the real population, as you saw because of all the metrics. And we have constructed a pipeline that you can use to generate your blips as many as you want. So what we want to do in the future is to generate lives to other type of glitches, and also to apply this to other methodologies like classification or anything that you can imagine. There's already this paper in our archive that explains the full procedure, and there's this other paper in PNP revision right now, which is a proceedings paper for a machine learning conference that tells a bit more about the coloring, resample, and how the package works. And last but not least, thank you so much for listening. And I wanted to thank all these people here because without their comments, this wouldn't be possible. Thank you. Any questions?
Can you hear me? Are there questions?
Great talk and great work. I'm interested in these metrics that we use for the anomalies. I'm wondering how homogeneous is the real population to start with? Do you also get sort of outliers in the real population that are as bad as the ones that you're against those are?
Yeah, actually, so because we are using Gravitational 5, we get a lot of repeating blips that are classified as blips, but they actually are repeating blips. So some of the generations actually you see that are repeating blips, and some other type of glitches. So we could actually do anomaly detection with the GAN, and it will tell us which glitches from the real population are very far away. Which actually that's some type of work that we wanted to continue because the GAN is there already. Thank you.
Other questions? Comments?
Hi.
Oh.
Thank you. Hi, sorry. So, hi, it's Agatha. We already talked during the Virgo week. I don't know if you remember, so I will ask you the same question, so you already know the answer. But the audience is different, so I guess it's useful.
The answer may be different.
I asked you last time if you applied this basically only to the blip, so it's one specific class, and I wanted to know if you plan to apply to other classes of bleach and how much time you expected.
Yeah, so I think we can do it for O2. We can apply to color fishes. That's kind of similar to blip in a sense. Repeating blips, I think also that's possible. But I think the main point here is to move to O3. because we have more data. So that's actually very relevant because GAN, they need a lot of data. But how long it will take? Well, I think Clayfishes can be quite fast because the data is already there. And we have a couple more classes that are already there. So those should be kind of fast. But moving to O3, that's something else. That's going to take a while. And thank you for asking the same thing.
So I was not asking any questions on the video. I will ask a question about the application to Einstein telescope, because it's very nice that you can rescale this to the sensitivity of Einstein telescope, but why do we think that there will be blip glitches in Einstein telescope?
Yeah, I think that's also a question that we thought about. So the problem that we have, well, I can tell you why we're using this in the first place, that it will give some context. So we want to build a classifier that's able to distinguish blitzes from cosmic strings, because they are pretty much filter functions, and they are really hard to tell apart. So the problem is that maybe they are not very good, like we don't have enough sensitivity nowadays. So we wanted to start with something easy, like a training set that is easy, and for cosmic strings with ET, which is going to be easier than, for instance, the O3 data, real data, right? So that's the first thing. The second thing is that even though we don't know if there will be blip glitches, we can expect short transients, blip-like in a sense. So they won't be the same, but at least we can make our algorithms robust to this very short transients that are very annoying and happen a lot. Right?
Yeah, some of the examples that you have shown, this glitch that B was really like a sine Gaussian, kind of a longish kind of, right? So this is still considered to be a blip or not really?
Not really.
Yeah, it's not very blippy anymore.
No, it's not very blippy. Blips are more like this tear form. That's according to the definition. So they look more like delta functions. They can also be up, like this delta up, and also that's also considered a blip. That thing over there, it's not a blip. That maybe will be useful, for instance, if you want to test your pipeline and crash it and put inside very crazy things like those. That might be interesting. Actually, some Tesla people are already interested in those.
Yeah, it's definitely very interesting to see what's the level of applicability, where there's a boundary of parameters when it has to work or stops to work. Yes. Nice work.
Thank you.
Okay, are there some other comments or questions? Okay, so we can continue over the coffee. Yeah, thanks.
Maybe you can turn it off.
So I will take it over.
I will flip this way.
Okay, so we have now one talk left before the lunch, but our speaker Velimir is somehow still not here. So this will be kind of difficult to have a talk Velimir. So I will take over and I will talk instead of him, and he will be talking after lunch. Okay, so let me. Let me do something not very standard. So what I wanted to do okay, so I will be talking about the denoising application, but as you can see, I didn't prepare a presentation. So I will be showing you this. And I'm quickly learning some Spanish here as well. Okay, so Can someone help me to make it kind of slightly larger? Maybe it's large enough. I don't know. Basically, that is supposed to can make it kind of wider. Control plus and plus is here. Because then it goes up and down. Okay, and I will be just moving the thing. Maybe you can stay like that, but then you just make it plus and thing. Yes. Okay. So I wanted to basically at the bottom line is that I want to ask you as a group for comments on this paper that we are working on with Philippe and with Agatha. And the topic of the paper is the denoising of gravitational wave signals from this usual already discovered binary black holes with a very, I would say, simple convolutional 1D time series convolutional autoencoder that has several dilated layers. So the initial results based on this were already presented at some point in Rijeka. And now we have finished this this work, and basically we would like to ask you, or maybe I want to ask you for comment because I'm not about my co-authors, but they are also probably interested in this. So the idea is that we have we took O1 data, and we also applied this to O1 detections. And also to O2 detections. So the idea is that we took noise from O1, injected artificially generated signals that we know how to generate because they are described by general relativity. We can kind of immerse them in the noise, prepare them as they were. They look exactly like real data in real noise. And then we have trained our detector, or denoiser actually. And then we were doing several tests on it, especially this one that we used the trained denoiser trained on O1 data, on the O2 data to check if it works. We trained it on one detector data, and we checked it on a second detector data just to check if this works, and I will show you some results. So on the Indico page, the paper is attached, so you can have a look if you would like to give us some comments. So I also would like to ask you about the kind of introductory part that basically describes the state of art, because maybe something we have missed. Maybe there is something that was already done concerning the noising of gravitational waves that we didn't describe properly. So if you could have a look at this, that would be very useful for us, because maybe this is not complete. Okay, so then we describe some so how the autoencoders works and how the denoising autoencoders work. So there is this kind of typical plot of the encoder-decoder structure with the latent space. In this paper, we don't use any latent space features, but in principle, it could be useful to describe some parameters of the compressed representation. So basically, we know what on the training stage, we know what the signal is because we generate it. We add it to the noisy data. So this is the corrupted input. And we then, in the denoising autoencoder, we request that the output is as similar to the clean input as possible. So this is basically described in the autoencoder. Is basically done by minimizing some sort of cost function Here it's usual, it's use the mean squared error. This is like that. Basically, the difference between the input and the output, because autoencoder basically compresses the representation. So it maps the input to optimally to itself, right? But this is how it's done. And in the denoised one, we want to remove the noise, so we want to have the difference between the input, the clean input, and the output as small as possible, right? And so this is the structure of the network. It has almost 20 layers. The decoder, the encoder, the decoder. This is the part when the bottleneck is this. Latent representation could be then kind of also additionally worked on. We don't do that here, but in principle it could be done. And there are several dilation layers that basically work like that, that the reach of the kernels is somehow dilated. They are not, the kernels in the convolution are not the usual one, but they're kind of spread around. So this, at least how I understand this, works like that, that this reconstructs this denoised version better. Another thing that we didn't do, but would also be done, we basically picked up the parameters, hyperparameters, and numbers of layers, and so on, basically using some sort of optimization, but mostly by hand optimization. We didn't do it automatically, like with some frameworks like Optuna and things like that. In principle, this is another thing that could be improved here, but it works kind of all right. Then here we describe how we prepare the data. So the data is the typical set of parameters that describe the binary system. Masses are taken from the that are consistent with the population of astrophysical black holes that we understand exist, between 10 and 30 solar masses, no spins, and we choose the distribution such that the signal to noise distribution is flat. So it's not astrophysical signal to noise distribution, but it's such that the noise learns all signal to noise more or less equally. So moving on. Okay, so here we describe what the signal to noise actually is, because we have to integrate the signal. It depends whether it's long or short, how we match the signal to the data to the template and things. The signals, the data is whitened, so that was already shown by Melissa. You have to normalize by the sensitivity of the detector, so that we are working. This, I think, is good for the neural network. It doesn't have to work with some crazy small numbers, but the numbers are always around 0 plus minus something. So it's like it's a normalization thing. It basically makes the frequencies that are not sensitive in the detector less important, and frequencies that are more sensitive according to this sensitivity curve, the ASD, amplitude spectral density, because we are working with amplitudes, not with power, PLD. This ASD basically prefers those frequencies that are more sensitive. So that's this, and this is basically one of the results. We have a injected signal to some sort of noise. This is a realistic noise from O1 from Livingstone, and this is the output. This is the denoised version of this signal with some estimate of the error that we make. This is the Alaratoric Uncertainty. It basically means that we immerse the same signal many times in a Gaussian noise and denoise it, and from the denoised version we calculate this envelope. This is more or less the definition of Alaratoric uncertainty. And then we make all kinds of experiments with it. One of it is what will happen if we denoise the pure noise without the signal. So this is the version, the noise version from this piece of data that doesn't contain the signal, because we want to compare if the denoiser actually knows what it's doing, right? It has to recover the signal. If it has only pure noise, it should recover flat 0, right? And it kind of does this, right? Okay. So moving on, I wanted to show you some results. So this is the MSE, mean squared error, versus the signal to noise. As you can see, this is more or less flat distribution of signal to noises. And this how this MSE is, how this recovered mean squared error is. So the colors described here are the distances. So this I interpret as the fact that it kind of learned various distances. The different signal to noises work more or less the same because it's more or less the smallest is better. So the majority, let's say, works kind of. Then there is something that we call overlap. So this is the overlap between the original waveform and the denoised one. Something that is mostly, often used in the gravitational wave comparison of waveforms. The overlap is basically this type of product, normalized by the input, by the original waveform, and this is basically a product of the input and the noise one, that is basically the output. So if the overlap is 1, then basically it's a perfect reconstruction. If overlap is 0, then it doesn't work. And so we study this. Most of the waveforms are well recovered, except the weakest ones, the smallest signal to noise, below, let's say, 8 or 9. We already start to see some problems, but this is expected. In one detections, this number of 8 signal to noise is something like a figure of merit. Below the 8 signal to noise equal to 8, things may happen because the signals are quite big. Okay, moving on. Then we tried to study the distribution between the injected signal and the denoised output signal. So this is supposed to be they're supposed to follow a line. X equal to y, basically, because if we perfectly denoise the injected waveform, then it should recover the signal to noise that is equal to the injected one. Of course, it's not like that because they are spread around and so on. Again, there are some waveforms that are very weak, small signal to noise that are not denoised properly, and so this is this blue histogram that basically shows the denoised distribution, and this red one shows the distribution of the pieces of data, but those that don't contain the waveform injected. So this is pure noise, denoised with the denoiser trained on the waveforms, just to show that if there is no signal injected into the data, it should more or less, ideally it should return 0, but it doesn't. It returns some sort of distribution, but the distribution ends more or less at 5. So more or less, one could then say, like, okay, if there is a denoised signal to noise of this waveform that is, let's say, larger than 5 or 6, then we have quite a high chance that there is really a signal there, not some sort of a fluctuation. The last thing that we did was we tried that on glitches. So we took glitches from O1. We took a lot of glitches from from Gravity Spy. Low frequency bursts, coefficient glitches, bleeps, and so on, and whistle glitches. These are some names. Basically, some of them visually look on spectrograms like a fish. That's why it's called koi fish. Bleep, you already saw, is kind of bleepy. Probably also it's related to the sound. Whistle is really literally a whistle because the frequency goes up and down, and you have this kind of sound, really. So we tried our denoiser trained on gravitational signals on those glitch data, and again we get histograms like that. with SNRs, denoised SNR, that they basically end more or less at 6. So again, we can say that the denoise is kind of robust against the pieces of data that are not containing any signal. So that's it. And okay, so there is also a description of the aleatoric errors. And okay, last but not least, the most important thing, real gravitational wave events. We tried that on O1 and O2, and it looks like that. Okay. So this is the famous 1509-14. It works very well because it's a very strong signal. This is the L1 Livingston. We used only Livingston data for training, but we also tried that on Hanford. We tried that in Hanford. So Hanford works slightly worse in this case. Then there was this is this is 1510-12. This is the let's say the weakest one. So we interpret this result. It's not very good, as you can see. Doesn't really work. We interpret this in such a way that the SNR is really low, and in L1 is 5 or almost 6. In Hanford is more than 6, but below 8. So the denoiser, in some sense, is maybe not able to really denoise this one because it's so weak. So we this is one of our failures in the sense, but we want to learn on this kind of failures. This is something that we expected that it will not really work. Then we have also tried that on the third one. This is 2612-15, and this one is also interesting because although the SNRs are quite, high enough, let's say for example almost 10 in Hanford, the denoiser didn't really work so well. It kind of produced like 2 pieces here and here, but because the waveform is so long, because the masses are lower than usual. They are lower actually. These are the masses 13 or let's say 14 and let's say 8, and we were training for more than 10 and 10 until 30. So here we kind of also can explain this in this way that this event is kind of outside of our training data, and the denoiser didn't really learn how to deal with such a long waveform. So that it kind of tried perhaps kind of to denoise 2 pieces, but somehow it failed in the middle because the waveform is long, because the masses are small. So we are having this type of happy accidents all the time. Then in O2 we have a bunch of nice denoised ones because the masses are correct and also SNR is high enough. Or correct in the sense that their masses are from our training data set. So it kind of works. Then there is some sort of weird thing here. Okay, this is to be checked. Then there was this case that in Hanford, I don't know if some of us probably remember 1706-08. It was detected only by Livingston because Hanford had a maintenance at that time. So the signal was later detected in Hanford, but as you can see, the data in Hanford is not really stable data. So what we did, we basically removed the low frequency part of the data and denoised it again. And this is the result. When we basically slightly shift the low frequency to higher frequencies, to basically remove the low frequency content, then we kind of detect it almost perfectly. So this is also a kind of a lesson for us to think about this denoiser and you can use it in different contexts. Okay, so sorry for this ad hoc impromptu presentation, but this is work in progress. If you would like to have a look at this, you're very welcome, and we are waiting for your comments. So thank you. And do you have any now questions or comments? Yes, we can talk. We can talk on the coffee break later.
Okay, thanks. So, and this, how do you get the reconstructed SNR? Is that something that the denoiser computes, or do you look at the time series and do another?
So yeah, so this is basically optimal match filter. Yes.
Okay, so the output is really just the time series.
Yes. The noiser doesn't really compute anything, just computes the time series.
Do you have any comparison yet what parameter estimation of the noise looks like?
No, we didn't do that. So this is something that we will do in the future.
But I guess that will be the interesting part.
Yes.
Do better after.
Yeah, for now we wanted to have something that is relatively fast, that can work kind of in low latency, produce output, generate triggers, and then it will become picked up by something more sophisticated. I don't know if is this switched on? Is it the microphone? Is it on?
No, yes.
Okay.
Yes, thank you. I've already seen some work which is kind of similar when trying to denoise some gravitational wave, and I know that proper denoise the inspiral part. So it's worked quite well for the major, but not that good for the inspiral part. Did you observe the same effect on your project?
So it kind of, as you can see, somehow works exactly like this, because the inspiral it's weak, the amplitude is the smallest. So I think it depends. One probably has to put more emphasis on the parameters that are being trained for. For example, probably we would have to put more low mass inspirals into the training data set, and basically, because since the short ones are working better than when one has to train more on this balance probably is something that one can think of. Yeah.
So first of all, if you just increase the SNR and as you mentioned, change a little bit the data set, it will work, I think. If you go for high SNR, so the inspiral is high enough.
I don't know. I would like to. I cannot promise anything because we already had all kinds of failures here. So it's you cannot guess this, I guess. It's kind of funny, but at least this is fast. So we are basically recently playing on the gw1 node. This is this bunch of V100s NVIDIA GPUs. And on this is really like you can just run it in 1 minute. You get the training, and then you basically play with it. It's very fast. It's pleasant.
I was just sorry. I want just what that I think it depends also a lot on the masses. I think
exactly.
Because how good and how long is the final phase? Okay, you understood the message.
Yeah, but also, so another thing is that one has to think about how we select the layers with the kernel sizes, because maybe this also something plays a role. That's what I mentioned with really carefully optimizing this, doing a really broad optimization set for hyperparameters, meaning sizes, some sizes and numbers of kernels, numbers of layers. What we did here, we basically experimented a little bit by hand, and we got something that we couldn't improve by hand. So basically, that is what we have. But in principle, with enough computing, one can just run this and go and make some tea and come back and it will be up by something like this. Yeah.
So I have maybe, I don't know, a stupid question, but have you thought going beyond O1 and O2? I mean, there will be differences in the data for sure, in the background.
So this is so because Agata was preparing the data, so I was of course saying, so yeah, of course.
It's the obvious. Of course, it's the obvious thing to do. The point is the time.
Okay.
Yeah, no, but also the number of events detected. So the easiest thing with O2 was all the events and checking for every 2 or 3 denoised states. So.
Yes, so the thing is that we already showed something that we wanted to show, that is that this method kind of has potential to generalize, because we were training one detector using this trained denoiser on data from a completely different words. So this representation in this sense is robust, or at least partially robust. So I think I would say that it would also work in O3. Why not? Yes. There's nothing really substantially qualitatively different.
I mean, at the end, the opposite, no? The data had more quality, let's say, so less.
Yes, but at the end, if you use this whitened data, well, you have Agatha. If you use whitened data, then the data is normalized by the sensitivity, so it always is this in the same, more or less, in the same unit. So yeah. Okay. All right. Let's stop for now. I think it's already past the time. We can go for lunch. Right?
I'm going to take your marker.
If you don't mind.
Okay, so, well, very, very interesting talks and questions and discussion. So yes, please, 2 things. We are now for lunch, so I managed this morning to get tickets free for lunch. So don't forget 2 things. One, put your signature for the people being online. Sorry, take your lunch at home. For the people here in person, please don't forget to put your signature of today attendance and take one of the tickets to go for lunch. So we are going to the Faculty of Pharmacy for lunch. We are going to close this room. So just give me 5 minutes to close everything, and I go with you to the lunch place. And we will be back at 2:30, so 1 hour and a little more for everyone online in person to come back. Hopefully Velimir will be also here, so we can continue with the program.
We will be sitting him down.
Yeah, yes. So he has missed the lunch, so sorry for him, but anyway. So see everyone at 2:30, and we can continue.
Yes, and then we have, because we have Velimir's talk, and then we have 2 talks. Yes, because we have the Velimir's talk from the room, and then 2 talks from remote, as far as I see from our schedule. Okay. Sure. Yes, we can always make it. Okay. Thank you very much, and see you in let's say more than 1 hour.
Yes.